Hello everyone. Today we are going to discuss the concept that is performing of AC analysis to the differential amplifier circuit. In this video you are going to see what is AC analysis and how it is used, and also what are the parameters that are to be calculated in performing AC analysis to one type of differential amplifier circuit. Here in the previous video you are seeing the DC analysis. So with the help of DC analysis to the differential amplifier circuit, you have calculated the operating point in order to know whether the transistor is operating in active region or not. Similarly, here in this AC analysis, it is used to calculate the small signal response of a circuit. Here, what do you mean by small signal means? This AC analysis allows you to figure out what happens to your circuit when you apply the millivolt signals without any noise. So, if you apply millivolt signals without any noise to the circuit, how the output response will be? What is the gain of a circuit? This will be calculated by considering a small signal responses to the circuit, that is, while helping out the H parameter, R parameter or the T model. So here, in order to find out the response or the gain of the circuit, these transistors are replaced either by the H parameter model or R parameter model or T parameter model. So in this AC analysis, with the help of H parameter model, we are going to calculate what is the differential mode gain and how to calculate it, common mode gain, how to calculate, and how to calculate the input impedance and the output impedance of one type of differential amplifier circuit. Here we are considering dual input balanced output differential amplifier circuit. So for this dual input balanced output differential amplifier circuit, and with the replace of these transistors to the H parameter model, we have to calculate what is the differential mode gain, common mode rejection ratio, input impedance and output impedance. Before entering into the calculation of all the parameters, first of all, discuss what is the H parameter model and how it is replaced with the transistor. Okay. Now here let us see for the single transistor. Here we are considered the type NPN type of transistor. The H parameter model of the BJT transistor circuit will looks like this. Here this base, and it is connected to HIE. Thereafter one voltage source HRE and the emitter is at other point, and the collector at the collector terminal we are having one impedance HOE and the current source HFE-IB. Here HIE represents the input impedance of the transistor, and HRE indicates the reverse voltage gain, HFE indicates the forward current gain, and HOE indicates the output admittance of the BJT transistor. Okay, so if you observe in the previous circuit, okay, so here what we'll do, simply we are removing this transistor and we will connect that H parameter model of the transistor to this circuit, and thereafter we will calculate the differential gain, common mode gain and CMRR. Okay, and here the HRE and HOE is not used when we are applying a small signal analysis, that is when a millivolt signals are applied as input to the transistor. That's why simply we are neglecting these two voltages and admittance. Now we are calling it as an approximate model of BJT transistor. Now we are considering this approximate H model of the BJT transistor circuit in order to calculate the gain and the impedances of differential amplifier circuit. Okay, so this is the final circuit that we are using to calculate the gain and impedances of the differential amplifier circuit of type dual input balanced output differential amplifier. So in the AC analysis, first parameter we are going to see is how to find the differential mode gain of dual input balanced output differential amplifier. So while performing AC analysis to the circuit, we know that the DC signals VCC and VEE should be kept grounded. That is, the VCC and VEE is grounded, and we have seen what is the concept of differential mode gain of dual input balanced output differential amplifier. Here the current flowing through the resistor RE will be 0. Why? Because these two are the input signals are same in magnitude but differ in phase. So here the 0 current will flow through the resistor RE, hence this RE will be 0, which means that it is kept grounded. Okay, so here this RE will be 0, mean there is no presence of RE, and it is directly connected to ground, that is 0 potential. And if you clearly observe, while performing analysis to this circuit, up to here this circuit looks like symmetry. Symmetry means this is the mirror image. Q1 transistor is nothing but the mirror image of Q2, or Q2 transistor is a mirror image of Q1. Why? Because here this Vs1 and Vs2 input signals are same in magnitude according to the theory. Okay, so with the help of theory concept of differential mode gain of dual input balanced output differential amplifier, with the use of center taper transformer, we are using the circuit in the half part as like this. Okay, so we are simply considering only half of the circuit. So here with the help of center taper transformer, these two signals are same in magnitude, means it is Vs by 2, and Rs we are considering the transistor Q1, and here there is no presence of Re, that's why here the emitter terminal is directly connected to ground, and at the collector terminal there is an RC and a DC voltage, simply a DC voltage is connected to ground. So for this circuit we have to perform AC analysis. Now how we are going to see AC analysis means, simply we are replacing this transistor Q1 with the H parameter model. Already we have discussed what is the H parameter model and how we have to draw this. Okay, now see a little glance. So this is the final circuit that we have taken for the performing AC analysis in order to obtain the differential mode gain. And for this transistor Q1, the approximate H model of this BJT is simply it is HIE and HFE-IB. Okay, so here if you observe this circuit, this transistor is replaced with this H parameter model, and at the base terminal if you observe, it is simply connected to the resistor Rs and Vs by 2. So externally this base is connected to the resistor Rs, okay, and the voltage source, that is Vs by 2, and the collector terminal C is externally connected to RC and thereafter ground, and here the emitter terminal is connected to ground. By connecting these external passive elements or active elements to this hybrid model, finally we are converting the circuit totally in H parameter model, and the circuit looks like, so this is the AC equivalent circuit. So for this AC equivalent circuit, the approximate H parameter model is, so it is Vs by 2 and Rs. At the base terminal we are having HIE and emitter is grounded. Similarly at the collector terminal it is RC, and one current source will be there, that is HFE-IB. So this is the final approximate H parameter model of AC equivalent circuit. So for this circuit, by applying either KVL, means Kirchhoff voltage law, or Kirchhoff current law, we have to find out what is the differential mode gain. So before finding out what is the differential mode gain, we have to discuss what is the differential mode gain. We know that the gain is nothing but output by input. If you are calculating the voltage, then the gain is output voltage by input voltage. Now what is the differential mode gain? Differential mode gain is nothing but output voltage by difference of input voltage. Okay, so that is the definition of differential mode gain. So finally here AD is V naught by VD, and we know this VD is nothing but the difference voltage, that is V1 minus V2. So before considering this circuit, we make an assumption according to the theoretical, that is the in the differential mode gain, the two input signals are having same magnitude but they differ in phase. So V1 and V2 are same in magnitude and they are different in phase. So it is one terminal voltage is Vs by 2 and the other terminal voltage is minus Vs by 2. So finally it is 2 Vs by 2. So finally we are obtaining differential voltage Vd as Vs. So Ad is V naught by Vs. So from this circuit we have to calculate what is the output voltage and what is the input voltage Vs. Okay, so if you observe, this output voltage V naught is nothing but the voltage drop across the resistor RC. Okay, so output voltage is nothing but voltage drop across the resistor RC, and here the current is flowing in the reverse direction. So what we have to do, we have to calculate the V naught in this direction, but the current is flowing in opposite direction, so we can write the V naught expression as minus IC into RC. Okay, so V naught is minus IC into RC, and now what is the final value of IC? So IC is nothing but HFE into IB. So this is the total current that is flowing. So IC is HFE into IB. Simply substitute the value of IC in this above expression. We get finally the V naught as minus HFE IB into RC. Now consider this equation as number 1. So finally we have obtained the value of V naught. Next step is we have to find out what is the value of Vs. So if you apply simply the Kirchhoff voltage law across this loop, we get an expression in terms of Vs. If you apply, then it is minus Vs by 2 plus Ib into Rs plus HIE into Ib plus 0 equal to 0. So finally Vs value are obtaining as 2 into Ib times of Rs plus HIE. So consider this as equation 2. Okay, so we have find out the value of V naught and Vs. Simply divide the equation 1 and equation 2. So if you divide equation 1 and equation 2, we obtain V naught by Vs as minus HFE IB into RC by 2 IB into Rs plus HIE. So the AD expression is IB gets cancelled. So V naught by Vs is minus HFE into RC by 2 into Rs plus HIE. We know that for the circuits the gain will be always positive. In that case we are considering only the magnitude. So AD is HFE into RC by 2 into Rs plus HIE. Now we are discussing this as, we are representing this as the differential mode gain for the unbalanced output. Why we are considering this differential mode gain for the unbalanced output? We are considering only the half circuit. Okay, so for the half circuit we have find the differential mode gain. If you consider for the total circuit, then the output voltage will be obtained as a potential difference across the voltages of collector terminals. We are calculating that as a balanced output. So for the balanced output, the differential gain is twice that of the differential gain of unbalanced output. By using this relation, finally we are getting for the balanced output signal, the differential mode gain is HFE into RC by Rs plus HIE. So this is the procedure how to calculate the differential mode gain for the dual input balanced output differential amplifier. Now next we will see how to calculate the common mode gain for the dual input balanced output differential amplifier. Okay, now the next parameter we are going to see is the common mode gain. So from the theoretically, the common mode gain is defined as the two input signals are having same magnitude and same phase. So literally these two input signals are equal. Practically we are calling it as a noise signals that are added to this differential amplifier circuit. Since these two input signals are equal, the output voltage obtained at this point will be 0. But because of practical biasing voltages and the current present at the transistors, this V0 value will be minute value, that is which is in terms of either microvolts or millivolts will be present even if there is an absence of input signals. Okay, so for this kind of circuit we are going to find the common mode gain AC. So AC for this dual input balanced output differential amplifier. So while calculating the value of AC, we have to consider the control voltage. The control voltage is nothing but the average of two input signals, assuming that these two input signals are same and are noise signals. Okay, now similarly what we have did in the differential mode gain, we are considering the same, nothing but we are considering only the half of the circuit. And also here while performing an AC analysis, the DC signals VCC and VEE will be kept grounded, and in the common mode gain there is a presence of input emitter resistance RE. Okay, so why? Because these two signals are same, means these two transistors are in on, and the current flowing through the resistor RE because of these two transistors will be of having same polarity. So finally the current flowing through this resistor RE we can write as 2 times of IE. Okay, so while calculating the differential mode gain and considering the half circuit, we are assuming that this transistor is also on and the current flowing through this RE will also be there. So it is 2IE. So if you draw the half circuit, then it looks like it is Vs and the resistor Rs. Thereafter the DC voltage at the RC will be grounded, and here VE value will be grounded, and the current flowing through the resistor RE is 2IE. Now from the basic definition, that is common mode gain is nothing but output voltage by input voltage. So here the output voltage is V0 and the input voltage is a common mode voltage signal or a control signals we are calling. So common mode voltage signal is nothing but average of two input signals. So average of two input signals, here V1 and V2 is nothing but Vs and Vs. Two signals are same. So finally Vc value is Vs plus Vs by 2, 2 Vs by 2, thereafter it is Vs. So finally we have to obtain what is the output voltage expression V0 and what is the input voltage expression by considering the approximate H parameter model of this type of circuit. We have seen how to draw the H parameter model. Just have a little glance. So this is the AC equivalent circuit that we have considered. So here the transistor is replaced by the approximate H parameter model. This approximate H parameter model is having only the H parameter, that is HIE and HFEIB. So replace this transistor by using a approximate H parameter model. Then the total circuit will looks like this. Okay, HIE, HFEIB. So at the base terminal we are having a voltages, that is Vs and Rs, and at the collector terminal RC will be there, and at the emitter terminal there is a resistor, that is RE. Here we can replace this 2 with RE, so we can write as IE and 2RE from the Ohm's law. Okay, now from this we have to write what is the output voltage expression V0 and what is the obtained input expression value. Thereafter dividing V0 by Vs, we can easily obtain the common mode gain. Okay, so as in the previous what we did in the differential mode gain, that is the output voltage is nothing but the voltage drop across the resistor RC. So since the current direction and measured output voltage will be in opposite direction, so we can write the V0 expression as minus IC into RC. Okay, and here the IC value is nothing but HFEIB. So finally the V0 expression we can write as minus HFEIB into RC. Now consider this as an equation 1. Okay, now simply apply KVL to the input loop. Now what is the input loop? This is the direction we have to apply the Kirchhoff voltage law. Now if you write the equation, then it is minus Vs plus IB into Rs plus IB into HIE plus here the total current is IE. We know the relation between IE, IB and IC. Nothing but IE is IB plus IC. So we can write as 2RE into IB plus IC is equal to 0. Now what is the value of IC? So here the IC value is HFE into IB. So simply substitute here the value of IC in this equation. We will obtain as minus Vs plus IB into Rs plus IB HIE plus 2RE into IB plus HFE IB. From this take IB common. So if we consider then minus Vs plus Ib times of Rs plus Hie plus 2Re plus 2Re HFE Ib. So finally we have obtained the Vs expression as Ib into Rs plus Hie plus 2Re plus 2Re into HFE. Now divide equation 1 and equation 2. Finally we will obtain the AC value as HFE into Rc by Rs plus Hie plus 2Re into 1 plus HFE. Okay, so here this Re is nothing but a feedback resistor or an emitter resistor. So if you increase the value of Re, then the denominator part will get increased and finally the common mode gain will get decreased. So if there is a decrease in the common mode gain, then the system performance will be better because of high common mode rejection ratio. Okay, so this is the procedure how to calculate the common mode gain for the dual input balanced output differential amplifier. Now next third parameter we are going to see is common mode rejection ratio, that is CMRR. So we know that the common mode rejection ratio is defined as the ratio of differential mode gain to the common mode gain. So CMRR is AD by AC. So for the dual input balanced output differential amplifier, while performing AC analysis with the help of H parameter model, that is approximate H parameter model, we have obtained the values of AD and AC. Okay, so AD is for the dual input balanced output differential amplifier, it is RC into HIE by RS plus HIE HFE, RS plus HFE, and AC is RC into HFE by RS plus HIE plus 2RE into 1 plus HFE. So simply substitute the values of AD and AC in this expression. So finally we are obtaining for dual input balanced output differential amplifier, the common mode rejection ratio is RS plus HIE plus 2RE into 1 plus HFE by RS plus HIE. Okay, so this is the procedure how to find out CMRR for this dual input balanced output. If you consider the unbalanced output, okay, so for the unbalanced output, what we have to do, we have to divide this AD expression by 2. So next we are going to say how to calculate the input impedance and the output impedance of a dual input balanced output differential amplifier. How to calculate the input impedance of dual input balanced output differential amplifier. As we know that the input impedance is measured at any one of the input terminal with respect to ground. Okay, now we are going to consider the approximate H parameter model of dual input balanced output differential amplifier. So if you consider this is the circuit, so for this circuit we have to calculate the input impedance at this point. Okay, so this is Ri. So we know that from the Ohm's law the resistance is nothing but R is equal to ratio of voltage to the current. So V by I. Here the voltage is Vs by 2. Okay, so V is replaced by Vs by 2 and the current is Ib. So finally the input impedance Ri we can write as Vs by 2Ib. By simply applying KVL to this input loop, we can find out the input impedance Ra. Okay, so if you see the input impedance Ra is Vs by 2Ib, by simply applying KVL as we did previously in the differential mode gain, we can obtain the Ib expression as Vs by 2 times of Rs plus Hie. Now simply substitute this Ib value in this equation, we will get Ra as Vs by 2 times of Vs by 2 into Rs plus Hie. These two get cancelled and Vs will get cancelled. Finally the input impedance Ra is Rs plus Hie. Okay, here we have derived the input impedance which is measured at any one of the input signal with respect to ground. Okay, so from this we can say that for the single input, the obtained input impedance is Rs plus Hie. If you consider the dual input, okay, so for the dual input we are going to have two input sources. So two input sources that are connected in series. So finally for the dual input we will obtain the input impedance Ri as 2 times of Rs plus 2 to Hie. Okay, so for the dual input, Ri is 2 times of Rs plus Hie. So this is the procedure how to calculate the input impedance of dual input balanced output differential amplifier by using an approximate H parameter model. Okay, at last we are going to see how to calculate the output impedance. Similarly, likewise the input impedance, we are going to calculate the output impedance, that is the output impedance is also measured with respect to the output terminal to the ground potential. Okay, so by considering the approximate H parameter model of dual input balanced output differential amplifier, so the output impedance is nothing but the output impedance that is seen at the output terminal voltage. So here V naught. So from this we can say that the output impedance R naught is nothing but the value of resistor RC. So finally the output impedance R naught is RC. Okay, this output impedance is same for all configurations of dual input balanced output differential amplifier. Thank you.